Welcome to my talk, Simplified Planner Selection. Over the last years, we have accumulated a huge set of planning problems. And at the same time, we invented a huge set of algorithms to solve those problems. But there is no single algorithm which performs well on all kinds of problems. Therefore, the problem exists, which algorithm should I choose to solve a specific problem? One way to tackle this problem are portfolios. In a portfolio, we're given a set of planners and a time limit. Most portfolios come up with a schedule. That means they select a subset of the available planners. They decide in which order they shall run them and how much time they will give to each of the selected planners. The idea is that most planners either solve quickly a task if they're good on it, or they will take a lot of time. And if I run a planner and it's not quickly solving the problem, then it might be better to try another one. Therefore, those algorithms select planners which are complementary to each other. The disadvantage is that if I have a hard task which no planner can solve in a short amount of time, then splitting up the runtime between multiple planners decreases our chances to solve this task. Instead, a second approach of portfolios learns a mapping. That means it learns a function that, given a task, tells us which planner to run, and then we use all available time on this task with a single planner. We will take a closer look at the second kind of portfolios. Maybe the most famous of those is Delphi, the winner of the 2018 IPC. In Delphi, you give it a task as PDDL file. It will construct a graph out of this task, either a problem description graph or an abstract structure graph. From the adjacency matrix of this graph, it will then create an image and scale it down to 128 times 128 pixel. And then it trains convolutional neural networks on those images to predict for a single planner whether it thinks the planner would solve the task or not. There are two problematic parts with this approach. The first one is the conversion to an image. Because we convert it to an image and scale it down, the question is what information is actually left in such a small image. And the second problematic part is the CNN. We have no clue what the CNN is actually learning. It works, and that's great, but we cannot understand what part of the image is causing the CNN to do the prediction. Our contribution is that we show that we can use simpler techniques and simpler features and still obtain a similar performance as Delphi. We show that our approach is robust to changes in the training and test data. We identify important features, and we investigate in which planners are selected by our models. A short background on the graph encoding. We're using the same graphs in the input as Delphi. First, the problem description graph. This is a graph modeling a SAS task, and we call later this version grounded. And every object in the SAS task gets a node in the PDG, and the relations between those objects are also encoded in the PDG. For example, the variables and the values of those variables in a SAS task are nodes, and there's an edge from variables to their values. The abstract structure graph encodes the PDDL task. It contains one root node for the complete task, and abstract structures are either lists of abstract structures or set of abstract structures or specific symbols. And in the case of a PDDL file, that means the root node is then defined as a list of abstract structures, and in this list is first an abstract structure for the operators, for the axioms, for the initial state, and for the goal, and then those abstract structures are further defined. As machine learning techniques, we use firstly linear regression. They use as input a fixed size vector with some values, and you learn for every element of the vector a weight. And the output of the linear regression is just the multiplication between the input vector and the weight vector. Secondly, we use decision trees, where you learn a tree. You start in the root, and every internal node contains a question. And if you can answer the question with yes, you go to the left child. If you answer the question with no, you go to the right child. And once you reach a leaf node, the leaf node will contain your answer. Actually, we later use random forest, which is just an ensemble of multiple decision trees. Finally, we use multi-layer perceptrons. Those are simple neural networks, where again the input is our fixed size feature vector, and those are propagated through the network, and at the end you get an output for every planner. Our training pipeline looks quite similar to the pipeline from Delphi. We get as input a task and then convert it either to an abstract structure graph or to an PDG. We don't do that anymore ourselves because there's a dataset published by Ferber et al. And this dataset contains a set of tasks, it contains the graphs for those tasks, and it contains the runtimes for multiple planners on those tasks. Instead of Delphi, we do not convert the graph to an image, but we convert it to some properties. We extract properties from the graph, like the number of nodes. And then we do not train a CNN, but we train our 3 machine learning techniques, linear regression, random forest, and MLPs on those properties. And we want that our techniques predict either the runtime of the planners on those tasks, or the logarithmic scale runtime, or whether the planner can solve the task or not. Every experiment is repeated 10 times. As input features, we use the following 9 properties. 5 of them belong to the graph. That means for a single graph, you get a single value, like the number of nodes. 4 of the properties belong to the nodes. For example, the degree. That means for a single graph, you get a value for every node in the graph. And as input to our machine learning techniques, we then use the minimum, the maximum, the mean, and the median values of those properties. Additionally, we augment our input features by once additionally providing them log scale to the machine learning techniques, because some of those feature values are very small and some features have values which are also very large. And we normalize the feature values in a range between 0 and 1. First, we compare our approach to Delphi. Therefore, we train it in the same setting as Delphi was trained. That means we use all tasks prior to the IPC 2018 as training data, and then evaluate on the tasks from the IPC 2018. For the different machine learning techniques, we also test different hyperparameters. For example, for linear regression, different L1 regularization weights. And then we obtain this wonderful table, which is way too big. Therefore, let's summarize it a bit. Every cell here is now the average over the different configuration of that technique. For example, for the linear regression with L1 regularization, this cell is now the average over the L1 weights from 0.1 to 5. Okay, on top is for the grounded graphs our performance, on the bottom for the lifted setting. And we see in the grounded setting, our technique works quite well. The models learn how to predict the right planner for the right task. And actually, we even outperform the Delphi baseline on the right. In the best setting, on average, we have 85% coverage, and Delphi, the original Delphi, only has 73% in the grounded setting. In the lifted setting, it does not look as good. It seems Delphi was better with the lifted graph. They learned more. It solves 86% of the task. Well, let's round it up to 87%. But our simple machine learning techniques with the features we extracted are working in general worse in the lifted setting. But overall, our best grounded models perform comparable to the best Delphi models. Evaluating only on the IPC 2018 task might not be a fair comparison, because different IPC organizers put a focus on different features. Therefore, we are now splitting the whole dataset into 10 folds, and in every fold we assign only tasks from the same domains. That means there is no 2 tasks from the same domain to different folds. And now we train our models on 9 folds and evaluate it on the 10th fold. Here we see that in general our methods still work very well. The coverage increases for all configurations except for 2. Next, we are evaluating which features are important for our models. Therefore, we are retraining our models, but we ignore some features. We're ignoring groups of features because there are some features which are highly correlating. That means one feature is, for example, always twice this value from another feature, and if we just ignore one of the 2, then the model will just use the other feature and still reach the same performance. Therefore, we first calculated which features are highly correlated, and then we are always ignoring groups of highly correlated features. And we see in the grounded setting the most important features as the maximum degree and maximum out degree. If we ignore those two features, then the performance drops by 60%, which is quite a lot. The second most important feature is the number of edges, and that's now just a drop of 5%. If we take a look at the lifted features models, there is no single feature which is as important as for the grounded setting, but we have also to keep in mind that the grounded setting performed better than the lifted setting. Again, the most important features are related to the degrees of the nodes. And interestingly here, there's also one group of features. If we ignore it, it improves our performance. The number of nodes and the number of edges are detrimental to the performance of the models. This can have two reasons. The first reason is that we are actually optimizing a different criterion than we're at the end evaluating. For example, we are optimizing for every planner to predict their runtime. At the end, we are just evaluating whether we selected a single planner which solved the problem. And secondly, our distribution of tasks could be differently. That means the distribution of tasks in the training data is different from the distribution of tasks in the test data. In the next step, we investigated in which planners we are choosing and whether we learned when to choose them. On the left-hand side, we see for our best performing linear regression model on the grounded graphs, which planner it has chosen. And we see that in 40% of the cases, this model chose Simba. In 25% of the cases, it shows configuration with LMCAT, and 20% one with IPDBs, and in 10% another configuration with petadatabases. And in total, this model chose only 7 different planners from the set of 17 available. The right-hand side shows us whether we learned when to select a planner. The vertical bar, for example for Simba, shows us what is the probability that Simba solves a task from the test states. That means in this case that if I give it a random task from our test task, that we have an 80% chance that Simba will solve it. The cross shows that what is the chance that Simba solves a task when we select Simba. That means if the model thinks Simba can solve the task, what is the probability that the Simba can really solve it? And here we see that for the 4 majorly chosen planners, our model learned when to choose them. Finally, we take a look at when a planner is selected. Previously, we just took a look at how often is a planner selected and whether it was right to select the planner. Now we take a look specifically for which task is a planner selected. The idea is that tasks from the same domain share some common structure, and that a model might learn also something about the structure and then assign a good planner, which might be good on the whole domain, to tasks which have some similarity to the structure. And here we have visualized it. Every block belongs to a domain, starting with Agricola on the left, then Caldera, and then in alphabetical order continuing to the IPC 2018 domains. Every planner has a different color. For example, Simba is brown. And we see for every task which planner was used. The top row shows for the lifted Delphi model which planners were chosen. And we see in 3 domains, Delphi was selecting only one planner that seemed to have recognized some similarities. But in all other domains, it's quite diverse, the set of planners it's choosing. There it does not look like it had learned something from the common structure to which planner to choose. Still, it often chose the right planner. And the bottom row, we see our linear regression grounded model. And this one seems to have better learned some common structure in the domains. In 4 domains, it shows only one planner. And in 4 other domains, it selected between 2 planners. In conclusion, we have shown that simple planner selection is possible. It matches the state of the art and it's robust to changes in the training data. We have shown that our models recognize the strengths of the individual planners and know when to select which planner. In the future, we want to switch to PDDL features as input because yes, the maximum degree of the nodes in this graph is better interpretable. We can think about what is the meaning of this, but it's still not intuitive. Instead, if we have as feature, for example, the number of actions in a PDDL file, it's way easier for us to understand. And we want to investigate whether we can use those models to understand why a planner is chosen and to understand what parts of the PDDL task make it easier or harder for a specific algorithm to solve a task. Thank you very much for your attention.